Good afternoon, everyone. How are you guys doing? Doing all right? Anyone went to ACL? No? I heard that Paul McCartney, instead of waving a Texas flag that he was supposed to do that, he waved a Chilean flag. I don't know if that's a true story or not. I don't know if you guys heard about that. But I think that's funny. No one going to ACL this weekend? No? All right. I never gone to ACL too, so we're in the same boat. All right. Okay, guys. We're going to continue talking about poroelasticity. And I had forgotten to bring the new project related to poroelasticity because we were still working a little bit on the finite element assignment. Are there any comments about the finite element project? Was that okay? You got to the answer that you wanted. Your analytical equation worked well compared to the numerical one.
Yeah.
Yes.
The analytical equation worked well.
Yeah.
The was okay, but its syntax is all sort of confusing for me.
The syntax is, yeah, I know it was totally for you, so I gave you that script that you could modify. Yeah, I think last year I didn't give the script, and they had to do everything from scratch. And I mean, you have the script there in the PDF, but I did it this year myself. Last year Igor did it, and I noticed that there were many small bugs that wouldn't allow you to run the script. So I think last year was much more difficult. But remember that you can use that software for any kind of solution of a differential system of differential equations. So go through the manual. You'll see it's very useful. All right, but and you can also solve poroelasticity there if you put the equations in the right way. So we're going to continue talking about poroelasticity, and our objective is going to be to calculate what is the variation of the stresses or stress path of a reservoir that is subjected to depletion. So over here you have a wellbore, and that wellbore is going to produce out of this formation, and you're going to have to calculate what is the variation of effective stress with variation of pore pressure. I'm going to ask you to use, similar as before, an analytical solution that hopefully we'll solve today. We'll get to that. And also I'm going to ask you to use a numerical simulator. And that numerical simulator is not the FreeFEM one, but we're going to use another software that we have here in the department, which is specially designed for oil and gas reservoir simulation, and it's called CMG. And that stands for Computational Modeling Group or something like that. So using that software, you're going to be able to use the theory of poroelasticity, and then you're going to compare those two solutions. But before you do that, you're going to have to calculate poroelastic constants out of a real experiment. I'm giving you the data here. So in order to solve this problem, then we have to compute what are the poroelastic constants of the rock. And after we know the poroelastic constants of the rock, you're going to calculate what is the stress path with varying pore pressure. Something very neat about this example and in general about this type of application is that usually in solid mechanics you change stresses by adding more stress. For example, you put a building on top of layers of soil and rock, or you put a hydraulic fracture and you prop the hydraulic fracture so it applies the stress on the rock. In this case, when you have a porous solid, we're going to be adding stress to the rock, but with no addition of total stresses. We're rather decreasing the pore pressure, and that decrease of pore pressure is the one that is going to increase the effective stresses. So we're not adding anything. Furthermore, we are extracting fluids, and that's causing the change of stress. Okay, so keep that in mind. We're going to talk today about the Biot coefficient, about stress path, and that's almost everything you need in order to solve this project. So we started with the theory on Thursday, and we talked about the porous solid and talked about a very important definition, which is the Lagrangian porosity, which, remember, it's a porosity which is defined with the original bulk volume. That is very important. We define also change of porosity and also work through the equations that allow us to compute what is the total bulk strain as a function of the solid strain and the porosity strain. And we found that that is simply a volume fraction equation of the solid part and the porosity part. So solid strain, porosity strain. And we worked through some examples of what is a solid strain and what is a porosity strain, and how you can change those two according to the boundary conditions. So very important now, remember that before, just for solid mechanics, we had two types of boundary conditions: displacement constraints, stress prescribed, and also now we have a third one, which is pore pressure. We can have constant pore pressure, or the opposite of constant pore pressure, that pore pressure will be closer to prescribed stress, constant pore pressure. The opposite of displacement constraint is going to be constant mass, constant fluid, and that's something that we're going to call later undrained loading, because the amount of fluid inside the porous solid is not going to change. Okay, we'll get there later on. In order to solve the poroelastic equations, we need to talk about the, if we work on a derivation based on thermodynamic energy derivation, we need to talk about the energy of the porous solid. There was a small mistake here in my previous notes. I fixed it now. So let me explain that. Any addition of energy, all this shaded area, is going to be a differential of strain times sigma, which is that. If you take the integral of that, and if you assume a elastic law where sigma is k times epsilon, the integral of that is going to be integrating on epsilon. It's going to be epsilon squared divided 1/2. So it's just an integral. So at any point over here, the total energy is this number over here. Strain squared times the, in this case, this is the bulk modulus. Okay, so we said that if we have a porous solid now, we have three ways of adding energy to the entire porous solid, counting the fluid inside as well. We can add a volumetric strain by means of the mean stress. Notice that shear stresses do not cause volumetric strains. That's that term over here, same as that one over there. We can add energy with shear strains, and this is a property of a solid. What is the difference between a solid and a fluid? Right, and a solid can bear those shear strain or stresses, right? So it's this term over here. And this is the deviatoric stress tensor This is the deviatoric strain tensor. And one more, we can add also energy to this fluid filled porous solid with pressure, pressurizing the fluid inside. And that's also going to be quantified by the change of porosity. If I change the porosity, I also add strain to the solid, which is going to add even more strain to the porous solid. So we have the energy that comes from the fluid itself and the energy that comes from deforming the solid. So based on this same equation, I'm going to define another very similar equation, which is going to be the free energy of the porous solid, but just of the solid, not of the solid filled with the fluid. It is filled with the fluid, but I'm going to take out that energy from the fluid part. And that's going to help me derive some of the equations that I'm looking for. And that energy, we're going to denote it with this eta, or eta, as you're going to call it, S, and that means just the energy of the solid. And if I consider a similar equation to this one, and instead of talking about differentials, I compute the total energy, this term over here is going to convert to 1/2 K bulk volumetric strain square, which is the same as that one, right? This one is easy to derive. The other ones take a little more work. So I'm just going to write them over here. This is the contribution of the mean stress. This is the contribution of the shear strains. So shear modulus now times the shear strains. Here I'm going to subtract the contribution of the pore pressure part. And notice that I'm going to introduce a constant that I don't know what it is, okay? I really don't know what it is. It's just a constant, but just for convenience, I'm going to set it as that, and I put it between parentheses, and that's going to depend on the volumetric bulk strain times the pore pressure, and there's going to be another component, which again it is just a constant, but just for convenience, I'm going to write it like this, and this is the contribution of the fluid. So it's the fluid with the solid, just the fluid. These two are unknown. And I'm going to assume that those are constant. Yes, Michael.
Why is it that we have the two E sub ij's separate and not like squared or something with G?
Because if you, this will be like an initial summation. It will mean that you will have to do E12 times
okay.
E12 plus G times E13 times E13.
I forgot they were.
So here I'm compacting many terms into just one.
Okay.
Okay, I have done an assumption here which I didn't have before, and it's important to say. You know which one it is? It's the assumption of linear elasticity. So going from here, from dW to here, I have assumed linear elasticity, and furthermore, I have assumed that I have an isotropic solid. Why? Because I just have two elastic constants, K and G. Bulk modulus, shear modulus. And something else I have assumed is that you see how similar these terms are. Like this is a modulus, and here this is considering it's similar to a square. So you see this one is a square here, and here I have P. assuming that this is just one constant, it means that, or this is a product, this multiplies this product, it means that this is also a constant. These two are constants. So not only the porous solid parameters are constant and go with linear elasticity, but alpha and n are also going to be constants. That's how I can build this equation from scratch. I could have done exactly what I did over here with all the terms, but that takes a little bit of work, and it doesn't really go into what we want to discuss in detail. Okay, so this is an energy equation. Quantifies how much energy you have in a porous solid saturated with a fluid at a given pressure and at a given volumetric and shear strain. You have a question?
Why is the last term squared? The dimension doesn't match.
This is a modulus. So it's going to have a unit of a pressure. So it's, at the end, is going to match. Everything is going to be in the units of pressure. Okay, so let's compare now this equation, which is an energy equation, total free energy equation of the solid, with this one. What happens if you take the derivative of energy with respect to volumetric strain? What do you get? So a partial derivative of this with volumetric strains. You get the mean strength, right? So similarly, if I take the partial derivative of this free energy of the solid function respect to the mean, the volumetric bulk strain, I'm going to get the mean stress, and which comes from over here, and that mean stress is going to be equal, according to this equation that I have written over here, is going to be Ke is the derivative of that respect to that one. And look, where else we have strain? Not here, not there, but we have one more over here, right? So minus alpha p. P, it's that's not influenced by, well, it is influenced, but it's not. We're assuming in this case it's it cannot be taken out from the derivative. So the only variable is that one. So alpha p, right? And if I take similar to now this one or to that term over there, I take the derivative of the free energy of the solid with respect to the shear strains, and I'm just going to get the shear stress, and which is in this case 2 times G, the shear strain. And if I take the negative of the derivative of the free energy of the porous solid respect to pressure now, no pressure here, no pressure there, I have a pressure here, and it is negative, so this is going to be alpha volumetric strain plus 2p, and that cancels out p over n. And I forgot to write this over here, but let me move this equation a little bit to the right, okay? If you look at there, do you see what, when we take the derivative with respect to pressure, what that's going to be? This is going to be the change of porosity, phi, and it's going to be what I just wrote before.
Shouldn't it be minus E because it's the minus there?
No, because in this case, if you took the derivative of W, yes, you'll be right. But we're taking derivative of this one, in which we already have a negative term. And these are the three equations of the poroelastic solid. So this one, it's something that we knew before. So mean stress proportional to bulk modulus times volumetric strain. But now we have an additional term for pressure. This one remains the same as we had before. Is a shear strain is equal to the shear stress times 2 times the shear modulus. And we have a new equation here for the change of porosity that depends on volumetric strain and also on pressure through these two coefficients. The question that now remains is, what is alpha? What is n? And in order to answer to that, we're going to run some virtual tests in order to find out what is the value of those two parameters. Okay, so let's start running these tests as thought experiments. I have a porous solid with all connected porosity. And let me clarify that. It's all connected. And I'm going to perform what is called an unjacketed loading. I forgot to bring one sample of rock sample, but usually when we run tests with rocks or with soils and we want to have a different stress to the pore pressure, we put it around a membrane. And that membrane, some people also call it a jacket. That allows us to have, so the jacket will be, if you have a sample with pores, usually here you put an end cap, here you put another end cap. Sometimes you may have a connection that goes in through the end cap to connect the pore fluid with pumps. And in order to apply an outside stress, you put a membrane around, which also is called a jacket. So in this case, we're not going to put any jacket around the rock. And we're going to apply, we're going to fill it with fluid, and we're going to apply a pressure P. All around the rock. And let me make a pore here on this side. The porosity is all connected, okay? So what do you think is going to be the pore pressure inside this rock? It's going to be P also, right? So this P inside the pore, it's also P. Okay, so let me label these equations. So it's going to be equation 1, equation 2, and equation 3. Let's use first equation number 1. Equation number 1 tells me that I have the bulk modulus here, volumetric strain, and this is what we're going to see later is called the Biot coefficient. And what is going to be the pressure? The pressure is just going to be just P, right? And what do you think is going to be the stress around the rock? Well, it's already a pressure, right? The total. It's just going to be P. But remember the poroelasticity, and just for the derivation of the equations, we are assuming that compression is negative. So instead of P, it's going to be minus P. So this is equation number 1 for the unjacketed loading. And from here, I'd like to calculate what is going to be the strain that I'm going to measure by doing such test. So if I do that, let's see, I have to move this alpha to the other side. So it's going to be 1 minus alpha P divided by K, right? And no, wait. This is going to be positive. This alpha, if this alpha is positive on the side, I want a negative, I need to add a negative here, okay? But I need the equation. It's more meaningful to write it like this, because we're going to see later that this alpha is less than 1. And because this alpha is less than 1, we don't know that yet, but I'm going to show you in a bit. If I apply a pressure with unjacketed loading with just pore fluid pressure from everywhere, what do you think is going to happen to the porous solid? It's going to get smaller, it's going to get bigger, or it's going to stay the same size? Smaller? Raise your hand if you say bigger. No? The same? Two the same. And smaller? Most people. It's going to get smaller, okay? It's going to get smaller, and the amount that it's going to get smaller is going to be P divided by K times 1 minus alpha. We don't know what alpha is, but the pressure is going to be positive. This is positive. It's going to be negative. A contraction, negative, as we are working with poroelasticity. Notice that here, if I were to subsample a small piece of rock, and I'm going to zoom in to do that subsample, say somewhere over here. What are the stresses on that solid? There are no pores over there, okay? So what do you think are the stresses in that solid? P on all sides? Well, but from the bottom side, you're applying P as well, right? And look, you have P from here, you get P over there, P from the top, P from the bottom. It actually has a stress, which is isotropic, and it's also P everywhere. So here, there, and there, it's also P, and it is a compression. So this is exactly the same as if you had no pores at all. If you had no pores at all, then also you will have, so if we draw the same solid, now with no pores, if we were to subsample, I'm going to draw it on one side, okay? But it comes from all sides, the stresses. If I were to subsample the same piece, it will also have P from all sides. And if I apply a pressure from all sides, the strain is going to be negative, and it's going to be a compression. Because of that same reason, the strain of the solid in the porous solid is going to be equal to P divided the bulk modulus of the solid. And now this is of the solid. This one was of the entire porous solid. Now this one is of the solid itself. Okay? And because notice that this is very similar to that one. In the pores, I have the same pressure, and it will be exactly the same as that. The bulk strain is also going to be, for this unjacketed test, equal to the solid strain, because these two loadings are the same. And because of that, if I put these two equations together, so now I'm going to have 1 minus alpha p over k is going to be equal to p divided by k, as I got rid of the negative signs, and the p is the same. I'm going to get that alpha is going to be equal to 1 minus k divided by ks. I have done another assumption here, which I didn't emphasize, but it's going to be very important to emphasize now. Something I said before, which is very important, is that all porosity is connected. Because, for example, if that pore was occluded porosity, I wouldn't have pressure from this side. And if I don't have pressure from this side, the pressure in this direction would not be P, would be 0. And that state of stress, that deformation inside that pore, is not going to be that one. So it's very important that for this, to get to this equation, all the porosity has to be connected. The second thing is that the porous solid is isotropic. It has some holes, but it is isotropic and it's the same solid everywhere. Again, if I had, say, a section here of the solid which is different from this solid over here, that will take more stress than the neighboring solid and will not make the state of stress homogeneous everywhere in the porous solid. And also, I would not be able to arrive to this equation. So I arrived to this equation. Again, I write it here because of porosity is connected, and because this is an isotropic and homogeneous solid. Once I do that, I can arrive to this equation that tells me that this poroelastic constant, which is also called the Biot's coefficient, is equal to 1 minus the bulk modulus, which is also called, so this is the bulk drained, or some also people call it dry modulus, and this one is the solid matrix bulk